Exponential functions are not exponents. What's an exponent? The degree, the power. That's an exponent. If you notice, up until now, if that's the exponent, what is this number down here called? The base. All of our equations up until now, the base has always been x. Exponential functions now look like this. You notice how it changes because now where's x? It's the exponent. Imagine trying to solve for x now, looking for the inverse. How would we do that? That's what this whole chapter is about. Because now we are looking at this equation. But there are two stipulations here. A has to be positive. The reason for why it has to be positive. Let's say we had an equation with -2 to the power x. This is x and this is y. X is 0, x is 1, x is 2, let's make these negative, and we have +1, +2. If x was 0, what's our answer? What's y equal? 1. Anything to the 0 power is always 1. If x was -1, what will we have? What we would have is -2 to the power -1, which is the same thing as 1 over -2, which is -1/2. If x was -2, the negative exponent on top means I bring it to the bottom. I bring that equation to the bottom. That's all negative exponent tells us. So what is -2 squared? 4. If x was 1, then we equal -2. If x is 2, then we have +4. What do you notice? It changes signs. Positive, negative, positive, negative, positive, negative. So what's the graph going to look like? Up and down, up and down, up and down. So that's the reason A has to be positive. Another thing, A has to be not equal to 1. Why is that? If the base is 1, what's the graph going to look like? A horizontal line through 1. Y is always going to equal 1. So that's boring. So now what we're going to look at the base being between 0 and 1 and the base being greater than 1. Those two conditions now will tell us what the graphs look like. So our functions can look like this, any one of these. Exponential functions can have any of these conditions, and any of these looks. Let's look at the graph. For our examples, we're going to use A being 2 for right now. It's the most common one to be used. So with this, since the base cannot be negative, where's our graph going to be? Which quadrants? 1 and 2. Because x can be positive, negative, and 0. But the answer, since this is positive, will always be above the x-axis. Unless there's a shift. Let's see what this graph looks like. So x can be negative, x can equal 0, and x can be greater than 0. It can be positive. So when x equals 0, what's the answer? 1. And that's constant. All exponential functions will cross through 1. Now, when x is 1, what is the answer? Yeah, only 1, so it's 2. When x is 2, what's the answer? 4. When x is 3, what's the answer? 8. So you see, it keeps on going all the way up there. When x is negative 1, what's the answer? So when y equals 2 to the power negative 1, the negative exponent simply means move it to the other side of the dividing line. So it equals 1/2. When x is negative 2, so we have y equals 2 to the power negative 2, which is 1 over 2 to the power 2, which is 1 over 4. So it's 1/4. And you'll see what happens. It keeps on going forever this way. You see the x-axis as a horizontal asymptote. It'll never touch it, but it gets infinitely close to it. This is what it looks like when a is greater than 1. Remember, it can't equal 1, but it can be greater than 1. The graph will look like this. The only thing different, it'll either change, it'll be, if the bigger a is, if a is 10, it'll grow much faster. It'll go from 1 to 10 to 100. So, and the smaller a is, if it's 1.1, 1.2, it'll be very shallow. All right. So that's when a is greater than 1. What happens now when a is between 0 and 1? Let's look at the graph. Remember, also, again, same thing. You'll never have negative answers. Your x's can be negative, your x can equal 0, and your x can be greater than 0, it can be positive, your exponents. So what happens when x is equal to 0? Let's say a is equal to 1/2. That's the easiest one to work with. What if we have 1/2 x, or we could have said 0.5x. These are both the same things. But in this case, it's easier if we put them in fractions to show you what's going on. When x is 0, what's the answer? 1. Again, it always crosses through 1. Let's look at the positives. When x is positive 1, what's the answer? If we have 1/2 to the power 1, that's 1/2. When x is 2, 1/2 to the power 2. Yeah, so it's 1 squared over 2 squared, which is 1 over 4, so it's 1/4. So we see on this side, it goes infinitely closer and closer to the x-axis, the horizontal asymptote. Now, at -1, what happens at 1/2 to the power -1? Well, the negative exponent means that we flip the fraction inside there. So that becomes 2 over 1 over 1 to the power 1, so it's 2. What happens when it's -2? So we have 1 over 2 to the power -2. The negative exponent flips the fraction, which is 2 over 1, and it changes to positive. So we distribute, so we have 2 squared over 1 squared, which is 4. And at 3, it becomes 8, and so on and so forth. That's what our graph looks like. So if a is between 0 and 1, it's a decreasing function. It's a decreasing function. The slope is all negative everywhere. If it's greater than 1, it's an increasing function. If it's greater than 1, it's increasing. So look at the properties of exponential functions. Where the stipulation is a has to be positive and a cannot equal 1. Is it a continuous function? Are there any breaks anywhere? It's continuous. Is it 1-to-1? Is it a function? Yes. It's 1-to-1. So every 1x equals 1y. What's the domain? Yeah. All real numbers, negative, infinity, positive. So use all any x you want, you can put it in there. What's the range? Yeah, so it's strictly greater than 0. So it's increasing if what is true? It's an increasing function if what? If a is greater than 1. And it's decreasing if a is where? 0. Between 0 and 1. Very good. Or if it's a fraction or a decimal. Does it have a horizontal asymptote? Where? No. The x-axis. Does it have a y-intercept? Always where? 0, 1. So these are we just talked about those, and they're pretty. Now you look at those, they're pretty obvious. Which is even more impressive is this. Before this morning, have you ever heard of exponential functions? Not really. You heard of exponents, but not real exponential functions, because those aren't really taught in high school. Oh. Example 3. Let's graph these. F of x is equal to 2x minus 1. B, f of x is 2x, all that minus 4. And C is f of x equals 5 minus 0.5 to the power x. So the first one, what do we notice about it? Right? It's greater than 1, so it's what kind of function? It's an increasing function. Is there a shift? The original function looks like this. What does this do? It's a horizontal shift because it affects the x value. So we shifted up to the right one. So now this is my new origin right here. So my y-intercept is at 1. It shifts over one space to the right. Your x-intercept shifts from here. I mean, your y-intercept shifts from there to there. How about this one? What's this one going to do? It's a vertical shift, right? Because this doesn't affect the x, it affects the y. So the original graph, again, looks like this. It crosses at that point there. Since this is a vertical shift, the whole graph shifts down 4 spaces. So the x-axis, the origin used to be here. 1, 2, 3, 4, down. The x-axis is now down here. There's my new origin. The graph is 1 over, the intercept is 1 over that. So the graph looks like this. Now, C is going to be a little bit different. 5 minus 0.5x. So let's do this like we did in transformations. The first, what's our base? 0.5x. What does that graph look like? It's decreasing. So it looks like this. Crosses through 1. Is there a horizontal shift? No, because nothing affects the x. So expanding from there, what's the next thing that happens? Are you sure it's a vertical shift? Then we have 0.5x. Why is it not a horizontal shift? Because it doesn't affect the x. It affects, once your x is done, this is done, it affects the whole thing, which is the y value, right? So what happens? It's a vertical shift. It shifts on the x-axis. It's like this now. It shifts down. It's a reflection. And then what? What does this number do? It's a horizontal shift. I mean, a vertical shift. It's a constant. It's outside of that. So we go up 5 spaces. So there's my new origin is at 0, 5. The intercept is that 1 below there. So there's my y-intercept. And the graph is decreasing, so it looks like this. Again, same thing. We have to break it up into pieces and see if it's a horizontal or vertical shift. Earlier this semester, we talked about an example of interest, simple interest. Principal equals rate, interest equals principal rate times time. Now we're going to look at something called compound interest. This is what banks actually use, where every day that they accrue more interest into your amount. This is what it looks like. A stands for annuity. An annuity is what your note is worth. If you go to the bank and borrow $1,000 and promise to pay them back in 2 years, is that note, are you still going to pay it back $1,000? No, you're going to pay them interest. The amount that the interest that's going to accrue over those 2 years and that initial amount, that's called the annuity. So I can buy that note. Let's say that your overall bill to the bank would be $3,000, which is very possible nowadays. You borrowed 1,000, you're going to pay back $3,000. I could buy the note from the bank, let's say for $2,000. They get the money back now, so they made $1,000 for nothing. You owe me all that money. You'll pay me back $3,000 for I just paid 2,000 for. I'm still going to make money, which is how these companies work. So P is the principal. That's the amount borrowed. R is the rate in which you borrow it. It's going to give it into percent, but you have to convert it to decimals. 6% interest rate or 10%. Nowadays, it's like 20, 25% interest rate, which is criminal. N is the number of payments per year. Are you going to pay quarterly, which is once every 3 months? Are you going to pay monthly, which is 12 times a year, or daily, monthly, weekly, whatever? And T is the time. How long will you keep the note? So here's our example. You borrowed $100,000 at 6.5% interest. Compounded semi-annually. What does semi-annually mean? What does semi mean? Half, two. Annually is twice a year. So you'll pay every 6 months. Let's see what it says. So A, give me a function of in T years. So how much will you owe in T years? We have $100,000. 1 plus N is 2 because you're doing it semi-annually. What's your rate? Your rate is 6.5%. Convert that to decimals, you move the decimal place 2 to the left. So it's 0.065. 2 times T. So this is what your formula would look like. This is when you sign your life away, this is what it looks like. The only thing that you have control over is how many years you want to keep the note. And it grows every year by more than 6.5%, because this is twice a year. It grows by that much. So you get screwed pretty quick. Right. So then it asks, what is if T is equal to 0, if T equals 4 and T equals 8? That's the only thing you change there. Because to be honest with you, if you do this on work, you'd figure out what this number is, take 0.065 divided by 2, add 1 to it. That's constant. It's going to stay there forever. Only thing changes is up here. If T is 0, what does this number become? 0. 2 times 0 is 0. This whole equation here, raised to the 0 power, becomes 1. So at 0, you owe us $100,000. At 4, now you have $100,000. 1 plus 0.6065 over 2. 2 times 4, and multiply that out. So you see, now this number here begins to grow. And then you multiply it by 100,000, it grows pretty quick. So let's see what that one looks like. So we have parenthesis 1 plus 0.065 divided by 2. All that to the power, where's my power button? Yeah. To the power 8 times $100,000. So after 4 years, you now will have to pay $129,157, $158. So you just lost $29,000 in 4 years. Let's see what it looks like in 8 years. So we'll do $100,000 times parenthesis 1 plus 0.065 divided by 2. Raise that to the power. That's 8 times 2 is 16. In 8 years, you now owe 166,000. Remember, your penalty now is 66,000. You borrowed 100,000. In 8 years, you're paying back more than half of what you borrowed extra. Think, this is only at 6.5% interest. Imagine if it was 12 or 13 or 14. So you see how fast this stuff goes really, really quick. Yeah, and the rest of these, well, I do have to show you one last thing. There is a value with this equation here. We come up to a value for, and it's called the environmental and exponential number, E. It's a constant, is what the value was. It's 2.7181 or 2.718281719 or something like that. It's a constant. It's like pi. We use that in biology and in physical sciences whenever we do any calculations, because this is what growth rate most happens in exponentially, which is the COVID, for example. Whenever you have what do you call those? When you have medical measles spread epidemics, they grow exponentially. They grow really small at first, then they shoot up really quick, and then they die off because everybody's sick already. You can't get anybody else sick. And that's where this number came into being, is to explain biological expansions and constriction. So, but the rest of these examples here is just plug in the calculator and hit answer. As you see here, it has an E right there. That's the constant. So you could raise that to any power you want to. E to the power 5 is that number, and so on and so forth. And that's the rest of it. So in the calculator, type in this, find this value. So, all right. So that's the end of that section. That's end of section 2. We're gonna do sections 3 and 4 tomorrow and 5. So we'll finish hopefully by Thursday. We'll finish the course by Thursday, which will give you guys a few days to start your work.